Well, I can see how this goes. I'll finish this up on Wednesday. And then I'm thinking we'll have. I was going to do 8-4 and 8-5. But I want to end the test at 8-3. And then what I'll do is I'll just start throwing problems at you on Wednesday for the extra time. So you solve it, and then we solve it together and see how you're doing. And then we just go back and forth and practice solving questions for the exam. And then Monday is all review. And then Wednesday is the test. This is the very last topic. It's either we're going to finish today or we'll finish before the end of the hour on Wednesday. So now...
On Monday is holiday, we still have class.
Oh, Monday's holiday?
Holiday?
Oh my God.
Hold on.
No.
So, let's just check.
Let
So if it's a Laney holiday, I will not be here. If it's not a Laney holiday, I'll be here. And of course, your attendance is always optional.
The last one.
October 8th. Now I got it scheduled.
Okay.
So double check. So whoever thought it was a holiday is double check.
I can check it right now.
Okay. Do you really think it is, or are you just playing with us?
Ladies holiday. The calendar. What day is it? What day?
According to my schedule, it's October 8th. I have a review schedule.
There's a holiday. But there could be a holiday.
It can be a personal holiday, which you're free to take yourself. But that way. Okay, so remember when we had the work contest? And you and I would pick weights up off the ground to different heights. Well, now we're going to have a balance, and the left side is going to be competing with the right side, and either the balance is going to tilt to the right, or the balance is going to tilt to the left, or it's going to balance completely. And first example. So from the balancing point, from the fulcrum, is on the right side, we go 5 feet away and hang 2 pounds. On the left side, we go 5 feet away and hang 1 pound. And what's going to happen to this balance? Is it going to tilt right, tilt left, or is it going to balance? It's going to tilt to the right. This is going to work more than that. So, actually, let's do this. And this person. So the right side will drop down to 1 pound. And the left side is going to drop down to 1 pound, but go out 10 feet. So if I have 1 pound at 5 feet on the right, and 1 pound at 10 feet on the left, which way is this going to tilt? Tilt left, tilt right, or they're going to balance? That'll be left. So the 2 points I want to make here is that if the weights are the same, it's the distance matters. The bigger, if the distances are the same, the weights matter. The bigger the weight, the more tendency it's going to have to tilt that direction. If the weights are the same, then it's the distance that matters. And of course, the interesting one is what if each side has a different distance and a different weight? So let's imagine that 10 feet away, we've got 1 pound, and then 5 feet away, we've got 2 pounds. Okay, so now the left side gets the distance advantage, but the right side gets the weight advantage. So the left side doubled the distance. The right side doubled the weight. Left, right, or balance? You are absolutely right. So one more, and then we'll talk about the principle.
What's the principal's name?
I don't even know. We'll talk about it if I can give it to you or not. So somebody has 3 pounds at 5 feet, and somebody here goes to 8 feet with 2 pounds. So the left side wins with the weight, the right side wins with the distance. Which way is it going to go? Left, right, or balance? I've heard left, I've heard right, and I've heard balance.
Multiply them. So 15 and...
Okay, so let's go back and
16.
talk. Right. Yeah, the correct answer is right.
You can just... never mind.
We can do it?
So you just multiply them?
Absolutely right. Okay, so the idea is, just like we did with work, is we're going to measure the tendency for the stuff on the right to tilt it to the right. We're going to measure the tendency for the left stuff to tilt to the left, and then we're going to compare those two. And what I want is, if I double the weight, I double that tendency to tilt to the right. And if I double the distance, I double the tendency to tilt to the right. So the expression that gets this is if I do 5 feet times 2 pounds, which is 10 foot-pounds, that's exactly the same thing as the 10 times 1 here. So the reason that we have a balance is the 10 times 1 on the left is equal to the 5 times 2 on the right. And this, the 5 feet times 2 pounds, is called a moment.
Oh.
I'm going to call it the right moment. Okay. So on here, what's the right moment? 16 foot-pounds. And what's the left moment? 15 foot-pounds. Okay. So the right side has a tendency that we measure as 16. So there's 16, there's a right-leaning tendency of 16. There's a left-leaning tendency of 15. The 16 is more than the 15, so it's going to tilt right. Make sense? Let's do, I'm going to do 2 things. So one difference between ordinary English and people speaking math is in ordinary English, we always like to use positive numbers. So for angles, it's 90 degrees counterclockwise or 90 degrees clockwise. In math, we don't want to put numbers on that, is we just use positive numbers to indicate one direction, negative numbers for the other. So what's 90 degrees clockwise for an angle? How do we write that? That's negative 90, right? So when we have 2 different directions the angle could go, we use positive numbers for clockwise, negative numbers for counterclockwise. Positive numbers for counterclockwise, negative numbers for clockwise.
Why is it counterclockwise?
That's a good, I have no idea. Yeah, so for some reason somebody needed to make that distinction. I would have guessed they would have gone the other way.
Or maybe it's because like right is forward and
I have no idea. I mean, it comes from, probably comes from the fact that we want positive y to be up. So if we start here, as you'd want to start tilting toward the positive y. But actually, I'm going to go with that. So if I go a positive angle, that starts taking me into the positive y direction.
It seems kind of counterintuitive.
Yeah, they had to make some. They had to pick one way. So that's what we decided to go with. And then also, you remember in calculus we talked about how velocity can be positive or negative? So I could have a velocity of 3 feet per second versus a velocity of negative 5 feet per second. What does a velocity of 3 feet per second mean? It's going positive, and a negative velocity is when it's going backwards. So in English, we'd say the speed is 5 feet per second, and then you'd have to indicate that you're going backwards. 5 feet per second is backwards. So we're going to do the same thing here. Is instead of talking about right moments and left moments all with positive numbers, is the moment here is going to be 5 times 2. And then we're going to work with signed distances. So negative distances are distances to the right, negative 10 times 1. And then the way we're going to see if something balances or not is it's going to add these two together. If these two numbers are the same, then the negative exactly cancels out the positive, and the answer is 0. On this one, this left side is a negative 15. The right side is a positive 16. That's a positive 1, so it's going to tilt toward the positive side. So let's do a more interesting one. Say again? No, this is still 8.3 is the longest section of the book. So 8.3 does two things. Is it does hydrostatic force, which we just finished, and what I'm leading up to. Actually, let me tell you where we're going with it. The second part of 8.3 is for finding a centroid. So what's going to happen is I'm going to have some interesting two-dimensional shape. Let's say it looks like this. And I'm going to lie it flat. And then what I want to do is find that point on the shape where the whole thing balances. So there's one point where I could put my pencil and the whole thing would balance. So what we want to do is find the coordinates of the balancing point. So that's why we're talking about balancing. The second part of 8.3 is about centroids, and that's what we're doing. So you can think about this as the number line. The fulcrum is at x equals 0. Actually, you know what? Instead of putting that distance, I can just decorate the number line. So at 3, we hang off 6 pounds. At 8, we hang off 1 pound. At negative 4, we hang off 5 pounds. And at negative 7, we hang off 2 pounds. And the question we're asking right now, left, right, or balance? So what we're going to do is we're going to calculate all the moments, add up all the moments. If we get a negative number, it tilts left. If we get a positive number, it tilts right. And if adding up all the moments gives us 0, then we know it's going to balance. First of all, make sure you agree that that is the calculation to find all the moments. Negative 7 times 2, negative 4 times 5, and so on. a -2, that's a 6. I get a -8. You guys agree?
Yes.
So left, right, or balance? It tilts toward the negative direction. So a more interesting question is if I decide there's going to be somewhere over here where I can put the fulcrum so it actually balances. When I put the fulcrum at 0, it's going to tilt left. If I move it to the left, there's going to be some point where I'm going to get the whole thing to balance. And x bar is what we call that x value where it balances. So x bar balancing point. And our job, of course, is to find that x bar. Let's just talk about some calculations here. So let's say it's not. But let's say our x bar was equal to -1. Is what's the distance from -1 to 8? 9. And if I was over here at -4, what's the distance from -1 to -4? It is not 3. It is -3. So remember, things to the right are positive. We're using negative distances to indicate distance to the left. So as I can think about that 9 as 8 minus -1. And I can think about this -3 as -4 minus -3. So in general,
Minus. -1. You said -3.
I did. -4 minus a -1 is -3. So if this is at -1, I should do it this way. So if this is at x equals x bar, and this is at 8, how do I calculate this distance? 8 minus x. Okay. And if I'm over here at -4, how do I calculate this distance? Okay, see, it's with sign distances, it's actually easier. You don't have to worry about flipping anything around or doing an absolute value. It's just always number position minus x bar. Erase this. So I'm going to start calculating the moments over here. And so I put my fulcrum at some unknown x value, x equals x bar. And then when I start calculating, I've got 1 times 8 minus x plus 6 times 3, or x bar. 6 times 3 minus x bar plus 5 minus 4 minus x bar plus 2 -7 minus x bar. So do you see those are all the calculations that I'd make if I'm calculating with the moment x equals x bar? And if I wanted these to balance, what would all those moments add up to? 0. This is essentially how math gets applied. Is we're trying to figure out something, so we convert it into math language, the answer to this question is the solution to that equation. And then you've got all the tools that you learned in your algebra class to help you find it. And I'm going to explicitly solve for this, and I'm not going to simplify. Because when we get to the x bar expression, I want to look at where all the pieces are. So I just distributed all those weights, the 1, the 6, the 5, and the 2. And if you want to skip some of these algebra steps, that's okay. I'll tell you where you want to write again. So what I did was I found all the places that have the x bar here. And I added those to this side of the equation. And then, notice I can factor in x bar out of all that on the right. And then I've got a convenient place for this. It is my calculation for x bar. Is 1 times 8 plus 6 times 3 plus 5 times -4 plus 2 times -7. And then downstairs, 1 plus 6 plus 5. And if you want to skip writing down some of the algebra steps, that's okay, but you should have this in your notes, so make sure you see where this expression comes from. One plus 6 plus 5 plus 2. That exactly came from the 1 plus 6 plus 5 plus 2 here. So this is the sum of the weights, or another way to look at it is total weight of the system. So where the denominator comes from x bar is just adding up all these weights. And then what's happening on the top? It's I've got 1 times 8, which 8 times 1, I have 6 times 3, 5 times -4, and 2 times -7. You see, those are exactly the moment calculations we'd make if we put the fulcrum at 0. So the fulcrum was at 0, this would be 8 times 1, 3 times 6, -4 times 5. So the top is the sum of the moments about x equals 0. Okay, so that's how we're going to do our calculation for x bar. It's going to be a fraction. The bottom is going to be either the sum of the weights or the weight of the entire system. And the top is going to be the sum of the moments about x equals 0. So how much calculus have I done since this part of the class started? 0. There's been no calculus. This is all algebra, right? Algebra and arithmetic. So let's make this a calculus problem. How do I do sums in calculus? Integrals, exactly. So we're going to do this idea. And instead of just having the weights at a few places, we're going to have a weight for every x value. And then when we add those up, we're going to be adding up with an input. So let me show you how this works. So what I want you to imagine is that you've got a bar here. And this bar I have in mind is it's got a changing density as I move to the right. So this left side is pretty light. And as I move to the right, it gets heavier and heavier, denser and denser. And specifically, is I'm going to measure this bar. X is going to represent how many feet I went in from the left side. And depending on the dimensions we have, there's different ways we can measure density. In this problem, density is pounds per foot. Some problems it's pounds per square foot, some problems it's pounds per cubic foot. Some problems it's people per square mile. That's my density measurement here. And the way I'm going to think about this is every x value along here is going to essentially be a little weight that's attached to this, where we start with the fulcrum. And then we're going to want to move it somewhere over here so it actually balances. It can be further this way than this way. So how many different weights do I have hanging off this shape? So you have infinitely many?
6.
A lot more than 6. Is every slice along here is going to be, draw a slice here. Okay. So every slice along here is going to contribute to a tendency to tilt right. So we're going to use that idea that we had before. X bar is the sum of the moments about x equals 0 divided by the total weight. So let's work on total weight first. What are the units for weight? Pounds, right. So in this one, we're measuring distance in feet. Our density is in pounds per foot. So the weight is going to be in pounds. So I'm going to take that entire bar, and I'm going to look at each slice. So here's a slice of this bar. So here's x equals 0. X is that distance. There's a little slice of the bar. So this is 1 plus x squared pounds per foot. And how many feet wide is that bar? X is this entire distance. That's an infinitesimally, yeah. So this slice of the bar, that slice is dx. What are the units on dx? Feet, right? It's a length. So times dx feet. So the weight of the slice is 1 plus x squared dx. How do I get the total weight? Add them all up. And now we're doing calculus, so we add up all the slices with an integral. Now we're going to do the moment of the slice about x equals 0. And so what we're going to measure here is the distance from x equals 0, that's a signed distance, times the weight. So for this slice, how far is it from x equals 0? X. And the weight we already worked out is 1 plus x squared dx. That's just the calculation that we did right there. So you're going to get caught up. And I'm going to use the calculation for the moment of the slice and then do the sum of them for the x bar right here. So sum of, I'm going to add them up with an integral, x times 1 plus x squared dx, 0. The calculus version of the problem we had earlier is if I have a bar of variable density, so different parts have different weights, where can I put my finger to make it balance? So how far over do I have to go to get to the balancing point? And we just did the calculation of the x bar, and the sum of the moments about x equals 0 divided by the total weight, and we can do each of those calculations. So that's it for the one-dimensional case. What's more interesting is how do we find two-dimensional centroids? So right now, we'll do the discrete one first. So what I've done is I hung an 8-pound weight at the point 3,2. I've hung a 4-pound weight at 2, -1, and a 3-pound weight at -1,1. And this is the top view, so imagine this is actually like this. And so if I just put my finger right at the origin, it would kind of tilt somewhat.